All right, last time we drew up the perfect blueprint for our program. Well, today it's time to get our hands dirty. We're grabbing our tools and actually building the machine, piece by piece. Welcome everyone to this explanation by Forge College. So you've got the blueprint, right? Now let's build the machine. We're about to turn all those diagrams and abstract ideas into real, tangible, working Rust code. This is where the magic happens. Okay, so our big goal here is to bring that design to life. Now, let's be clear, by the end of this, we're not going to have a full-blown Solana program. Not yet. But what we will have is something maybe even more important, a solid, testable Rust crate. Think of it like a perfectly built skeleton that we know is strong and reliable before we add anything else to it. Our machine is really made up of 3 core components. First up, we've got instructions.rs. This is our control panel. It's the thing that takes all that messy input from the outside world and figures out which levers to pull. Then there's state.rs. That's the engine block, the absolute heart of the program holding all the critical data. And finally, we have utilities.rs. This is our custom tool workshop, where we'll forge all the specialized little helpers that make the whole thing run like a dream. So let's dive into that first component, the control panel. The whole job of instructions.rs is to take this raw, sometimes jumbled stream of data coming into our program and translate it into clear, understandable commands that the rest of our machine can actually work with. And this table here, it shows our parse instruction function in action. It's basically a super smart translator. See, it just peeks at the very first byte of data that comes in. If it sees a 0, it knows, okay, I need to read the next 8 bytes as a number for an increment command. If it sees a 1, that's a reset. And what if the input is just garbage or totally empty? Well, it's smart enough to just say none, basically acting as a bouncer at the door, keeping out any invalid commands. All right, the control panel is built. Now we need the engine block, right? That's state.rs. This module is really the heart of our machine. It's responsible for holding our program's core data and maybe even more importantly, protecting it. And that brings us to a really important idea, the invariant. It sounds fancy, but it's just a rule, a non-negotiable condition that your data must always follow for the program to be valid. You know, like a rule that says a counter can never go above 100. Our validate method is basically a dedicated security guard. Its only job is to check this rule every single time the data changes, making absolutely sure our program stays in a good, valid state. And last but not least, we've got our workshop, utils.rs. This is where we build all of our small, reusable helper functions. You can think of them as our custom tools. You know, things like a specialized math function that other parts of the program might need. Doing this keeps our main components, like the engine block, really clean and focused on their specific jobs. Now, inside that workshop, we use a really cool Rust feature for smart design, pub crate. When we label one of our tools with this, it's like putting a big sign on it that says, for internal use only. It means any other component inside our program can use it, no problem, but it's totally hidden from the outside world. This creates a really clean and secure boundary for our machine. Okay, we've done it. We've forged all the parts, the control panel is ready, the engine block is built, our custom tools are sharpened. Now, it's the moment of truth. Let's put this whole thing together and run some diagnostics. Let's see if our machine actually works. Our assembly process is actually pretty simple, but it's super powerful. First, we run cargo build. That's the command that bolts all the pieces together. Then we run cargo test. This is like our quality assurance step. It triggers every single diagnostic test we wrote to verify that each and every component is functioning exactly the way we designed it to. And look at that. That beautiful, beautiful line, test result, okay. You have no idea how good that feels to see. This is a huge milestone for us. It means our control panel is parsing correctly, our engine block is holding its state, our tools are working, every single part is doing its job perfectly. Our machine has officially passed all its internal diagnostics. Of course, you know, in the real world, they don't always work on the first try, and that is perfectly okay. It is absolutely part of the process. So let's talk about what happens when we need to tune the machine. Let's talk about how to interpret the feedback we get from our chief mechanic, the Rust compiler. Because this is the question every single developer asks at some point, right? But what if it all goes wrong? You run the build, and instead of that beautiful OK message, your screen just explodes with red text. What do you do then? The absolute key is learning to translate the compiler's messages.
I know, they can seem a little grumpy, but they're actually incredibly helpful. Like, look at this one, failed to resolve. That's not the compiler yelling at you. It's really just asking a question. It's saying, hey, I can't find this tool you're asking for. Did you maybe forget to import it with a use statement? It's not angry, it's just trying to help you fix the blueprint.
So here we are. We have a working prototype. And through this whole process of building it, we've actually uncovered some really fundamental principles of solid engineering. And these are ideas that apply way beyond just this one project. And these principles, they're simple, but they are so powerful. First, craft small testable parts. It's always easier to check if one little gear is working than to diagnose an entire engine. Second, make visibility explicit. Using things like pub and pub crate creates those clean, strong boundaries. Third, you've got to trust your tests. They are your safety net, allowing you to build and make changes without being afraid of breaking everything. And finally, remember the compiler is your friend. Yeah, maybe a grumpy friend, but it's honestly the most helpful one you've got. So think about what we've accomplished. We've built and we've tested our core logic. Our machine runs perfectly right here on the workbench. So there's really only one question left. Your core logic is solid. Are you ready to connect it to the blockchain? This explainer was made by Forge College. And hey, if you're ready to dive even deeper into this stuff or any other Web3 topics, you should come visit us over at forge.college. We'd love to see you there. Thanks so much for watching.